Let's add the nacho. Yeah. Do you have a USB-C charger in your phone?
I'm using it. Sorry. Let's look at this document that I handed out last week. That's okay. The whole point is actually to do it together. And we did not do it together. Anybody else need one? Good. Yeah, it is uploaded. I lied when I said it wasn't last week. Fooled everybody. One thing that I want you to be able to do on this is look at a structure and decide, is it aromatic, anti-aromatic, or non-aromatic? And I do want to clarify something to that extent. Sorry, you can ignore this. Because it's OChem 1 material. Not for you, apparently. It's not up to you, you're right. When you look at a structure that has an aromatic ring, then we say that the molecule is aromatic, and that can confuse people because if there are long linear chains, then most of the molecule is non-aromatic. So one way that we get around this is by saying that it has aromatic character. And that means that we can have anti-aromatic character as well, where a compound has an aromatic ring, or sorry, an anti-aromatic ring, and also things that are non-aromatic. And there are some structures where you can actually have all types of character. So, I want to give a few examples. You all remember benzene, and you remember cyclobutadiene. Which of these is anti-aromatic, if either? Cyclobutadiene. Notice I've drawn it with just that circle. Bad, because you don't know how many pi bonds are in there. It's confusing. But there's no charge, so really it works out. There's 2 pi bonds. Assuming that this is planar, cyclic, fully conjugated, this is anti-aromatic. This is aromatic. If I have a molecule, benzene, and I'm going to add to this, benzene with a methyl group coming off. We can say the molecule is still aromatic, but it's more common to say that it has aromatic character. The methyl group is not aromatic, but there is an aromatic portion. So this has aromatic character. In the same way, I can have cyclobutadiene with something coming off, and I can say the molecule has anti-aromatic character. So now, what happens if these 2 portions are connected by a chain? Does the molecule have aromatic character?
Yes.
Yes. Here. Does the molecule have anti-aromatic character? Yes. Here. So I want you to feel comfortable saying that certain regions of a molecule that are aromatic make a compound have aromatic character, and any regions of a molecule that are anti-aromatic make a molecule have anti-aromatic character. It's rare for us to say that a compound has non-aromatic character because that's not very interesting. That's like everything else. So we point out if it has aromatic or anti-aromatic character. And here, it has both. And now I actually remember what I needed to finish up. We weren't quite ready for those sheets, and that is on polycyclic structures. This is a polycyclic structure. It has 2 rings in it. But those rings are not related to each other in any way. Their pi electrons don't impact each other. So we're going to classify here and say for fully conjugated ring systems, that means it's not just one ring that is fully conjugated, like benzene or cyclobutadiene, but it's when all rings are conjugated with each other, ring systems. All pi electrons must be counted. You cannot ignore any pi electrons. Yes, sir.
So is it important to call something that's not aromatic non-aromatic?
It is important to call something that is not aromatic non-aromatic.
Did you mean to say that when something's aromatic, you have to mention it?
Yeah, and say that it has aromatic character.
Okay, but you don't.
Like benzene has aromatic character and nothing else, so we just say it's aromatic. But this compound has benzene on it, among other stuff. So this compound has aromatic character, among other stuff.
So describing any of the molecules, you would say that's aromatic, and if you don't say it's aromatic, then you assume it's not aromatic?
If you don't say it's aromatic or anti,
Oh.
yeah, then you would just assume it's non-aromatic. Unless you're being asked to label it, and then you have to choose. These 2 ring structures are fused. They are fully conjugated ring structures. Many students will take this structure on the left. It looks like benzene, if you cover up this right-hand side. It looks like cyclobutadiene, if you cover up the left-hand side. Well, they know that benzene is aromatic, and they know that cyclobutadiene is anti-aromatic, if it can exist. So then what does the whole structure become? Many students will just ignore this part of the ring, count benzene, call it aromatic. But for ring systems that are fully conjugated, that means every atom in the ring system is at least sp2 hybridized, then you have to count all of the conjugated pi electrons. So that's 2, 4, 6, 8 pi electrons in this system. I can't discount any of them. 8 pi electrons follows what rule? 4n. Not 4n plus 2. Which means that this compound has what kind of character? Good.
So with that, like, so when you have butadiene and there's this weird stretching, squashing stuff to make it non-aromatic, what does it do here in this method?
Well, first of all, that pi bond on the little 4-membered ring is incredibly reactive. So if you can form it, it's going to be hard to keep it stable because it's going to want to react in some way.
And there's not much stretching you can do with the benzene right next to it.
Yeah, it's definitely a little, it's locked for sure, but it may be able to distort. It may be stable by distorting itself and trying to break some of that conjugation.
Okay.
Do you remember last week I brought up how heteroatoms change their hybridization against expectation? And I gave some key examples of them. The pyridinyl nitrogen, that's the nitrogen in pyridine. That's benzene, but with a nitrogen in it. That hybridizes as you expect. But the nitrogen in pyrrole and the oxygen in furane, those look like they're sp3 hybridized, but they take on sp2 character. How would you label this nitrogen? Is it pyridinyl or is it pyrrolium? I made up those words.
Which one's SP3?
Pyridinyl is not sp3 and pyrrolium is not sp3. Pyrrolium is the one that looks like it would be sp3, but by being sp2, it allows for an aromatic compound to exist.
That's not SP3? If that... Yeah,
If this is sp2, an aromatic compound exists. If it's sp3, then the entire structure is not aromatic.
why does that pi bond affect it if there's no double bonds by it? Or P shell, not pi bond, sorry.
I'm not sure I can answer that, so I'll come back to that. First of all, how many pi electrons if the whole atom, or excuse me, if the whole molecule is fully conjugated? This nitrogen's lone pair, localized or delocalized?
Localized.
Delocalized. It does not belong to nitrogen. Nitrogen shares it through a pi system, which means nitrogen is what hybridization? sp2, despite the fact that all of your gen chem skills tell you it's sp3. That means that this lone pair counts as pi electrons. Delocalized, part of the pi system. How many pi electrons? 2, 4, 6, 8, 10. What equation does that follow? Where n is 2. 4n plus 2, 4 times 2 is 8, plus 2 is 10. What does n mean? Nothing. Garbage. Well, it's a solution to a problem. A means to an end. This is in, what character does this have?
Aromatic.
Aromatic. Good. Killian, I think you had your hand up first, then Jamie.
Would, if you had a double bond instead of a hydrogen off the nitrogen, would that still be aromatic?
Okay, actually, this was the next structure I was going to draw as a quiz for you all. We can do this 5-membered ring. All charges are shown. This compound is aromatic. How many pi electrons in the system? 8 would make it anti-aromatic.
So,
Additional lone pair.
carbon 3 on the 5-membered ring. Or I guess, whichever we want to have it. Does it not have 2 hydrogens on it?
No, everything's shown. If hydrogens were missing, there would be charges.
So would that make it sp3 then?
What?
Well, yeah.
The
Yes.
yeah.
That atom is sp3, which means the ring system
Is not aromatic.
not fully conjugated.
Okay.
So I don't count all pi electrons in the ring system towards aromaticity. I only count pi electrons that are fully conjugated. So that actually brings me back down to just these. Not part of fully conjugated ring.
So if you have 2 20-member carbon rings, so 40 carbons,
Yeah.
or 38, and stuck together, this one could be all the way conjugated, but this one is all the conjugated except for one alkene, is an alkane. That just completely ends the whole.
Count all the other ones. If there's just one part of one ring that's missing full conjugation, just count all the other ones.
But it.
And Jamie, did I answer your question yet?
No, I was gonna ask about that. Those nitrogen electrons being considered pi electrons. The lone pair of nitrogen.
Can you say it one more time? Why do we count this lone pair as pi electrons?
Well, I was trying to figure out in my head because like I'm thinking of the MO, not MO. This would be like
The frost circle?
I'm thinking of. So So that
By the way, I won't have you draw frost circles for polycyclic structures. Just monocyclic structures.
So I'm thinking like this. Those, we want them to be pi electrons. They have to be from an unhybridized p orbital.
Correct.
Which means it only has 2 hybridized p orbitals, which it has to be sp2.
Correct.
But why are the other 2 p orbitals hybridized? I only see. I'm just kind of confused.
It's also hybridized with S.
Yeah.
So I get sp2 orbital for a sigma bond, sp2 orbital for a sigma bond, sp2 orbital for a sigma bond, and I'm left with unhybridized p for the lone pair. P, 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 P. Everything has a p orbital conjugated.
I'm thinking like the nitrogen. So it's forming 3 sigma bonds. That nitrogen.
Correct.
It's forming no pi bonds.
Yes, it has a pi bond. Bond line structure can't show it to you.
That nitrogen has a pi bond.
It does. It's part of an aromatic system.
Delocalized pi bond. That's right. Okay. That's right.
Because bond line what? Sucks.
Hey.
Okay, so if you're looking at, like, say you're looking at the top structure on there, it was presented to us in a 3D space. Do we still have to determine errors? Does that make sense? So you might have a completely flat 6, and then you have something coming up over the top. Do you still determine the aromaticity of this bottom one, or is it now dense water because you have this, like, little bridge? Does that make sense?
Maybe. Most of the time when you see bridged bicyclics, they look like this.
Mm-hmm.
But this can't be benzene.
Yeah.
The bond
it's
angles don't work.
It's still there. But I've had a few where I've seen like fully double bonded and they'll have something go like 4, like 2 carbons up here.
Yeah, so we could take benzene, and I'm going to try to draw it kind of flat here. So this side is coming towards us. We could draw benzene and then have this kind of structure that goes up and over.
Yeah. So then would we just ignore the up over the top structure, or does this even matter for us?
Yeah, you're not going to see it.
Okay.
But you would just ignore this because there's no way it could be fully conjugated.
Okay.
The reason it can't be fully conjugated is the pi bonds. If even there were pi bonds all the way through this, the pi bonds would be at 90-degree angles to the pi bonds of benzene, so they would never overlap.
And so
They can't conjugate.
Okay.
Correct. Cameron. And then the urine.
Going back to the lone pair that's on the NH over on the other side of the board.
Yes, which is this lone pair that you can't see because it's delocalized.
So my question, if that other double bond on the 5-member ring wasn't there, would that lone pair become localized?
So you're kind of thinking about this, but
That would force it to be sp3.
changing it to be this instead. Pi bond's gone, but the nitrogen is there. Tell me.
So my instinct is to say that that lone pair is localized to the nitrogen.
Good.
So that molecule would have aromatic character with the left side benzene being there.
Yes.
The overall chemical or the overall molecule is not aromatic,
Correct.
right?
Or no, the overall molecule has aromatic character.
Okay. But it's inaccurate to say that the molecule is aromatic, or because it
No,
has
that's also correct. It's also correct to say the molecule is aromatic and it has aromatic character. I would say it's maybe incorrect to say the molecule is non-aromatic because it's just this portion of it that is non-aromatic. It has both character. That's okay.
Do we use this terminology or this naming the same way that we would with chiral? Like chiral can be part of a molecule, but it's not.
Yes and no, because you would never say this molecule has chiral character. It is chiral or it is not chiral.
You could have a massive molecule with just one chiral center, and it's chiral.
100%. And there are many, many medicational drugs that are huge molecules, one chiral center. This is kind of a good way to say that chirality is not the same as aromaticity, in that this is one molecule. We would call this one 1-phenyl 3-cyclobutadienyl propane. And I said that wrong actually. 1-cyclobutadienyl 3-phenyl propane has both aromatic character and anti-aromatic character. But you can't have a compound that has both chiral character and non-chiral character, because the character we're talking about is energetic stabilization of electrons or energetic destabilization of electrons, whereas chirality is how it interacts with light, how it takes up space, stuff like that. You can't have both characters at the same time. These are all great questions. Oh, Nira first. I'm so sorry. Nira.
So just going back to that top, yes, right there. So we say that it still has aromatic character.
Correct.
The only reason why the other one didn't have is because of that sp3 carbon, and it's not fully conjugated.
Yes. This 5-membered ring is not fully conjugated, which means I won't count any of the pi electrons that are just in this 5-membered ring towards the aromatic count. Same thing here. The nitrogen is no longer fully conjugated in this aromatic ring because of these 2 sp3 carbons. So I will not count nitrogen's lone pair. It's not necessarily correct to say that the nitrogen is not conjugated still. We can draw a resonance form, albeit one that increases formal charges, where nitrogen creates a double bond here, pushes out this pi bond as a lone pair into the ring. And we're going to leverage that in the next week as to why certain structures react in specific ways. Because these heteroatoms can still donate their electrons to a ring, and that changes the character of the ring. But these electrons are now localized to nitrogen. This is the major resonance form, and they are not part of an aromatic or anti-aromatic system.
Why do you need to be fully conjugated to have aromaticity? Why can't you have a ring and a half?
Like this.
Mm-hmm.
This is aromatic.
Yes.
This part is non-aromatic.
Why can't you have half of an aromatic?
Half of an aromatic
Mhm.
doesn't make sense. The rules are cyclic, planar, fully conjugated. If it's cyclic and planar but not fully conjugated, the molecular orbitals that can now exist don't grant that same energetic stabilization that these molecular orbitals have. You'll have to go into inorganic chemistry or physical chemistry to learn more about why those molecular orbitals are allowed, how to quantify their energy levels, and then prove that aromaticity is stabilizing. Take a look at this structure on here. This is called coronene. You can see that this is cyclic, planar, fully conjugated. What do we not know about it? We know that they must be double bonded because it's flat. So they're all sp2. What we don't know is how many pi electrons are there. So we could fill them in. We'd have to be a little systematic about it. Let's say that we did 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, and I feel like I messed up somewhere, right? That's what's really hard about this. What we can't do is say 6, 12, because these are sharing electrons here. These are sharing electrons here. It'd be easier if it actually had the number of double bonds, and then we could just circle all of the double bonds. But what do you suspect about coronene? Aromatic or anti-aromatic? What would your guess be? Anti-aromatic? Anti?
Oh, could I say non-aromatic instead?
You can say non-aromatic, but that would be a bad choice.
Oh.
Anti? Really? Do you notice how it's just a bunch of benzenes fused together? That's always going to be aromatic.
It's 4 and 8.
Do you remember? No, it's not. It's going to be 4 and plus 2.
What? Is that 24?
I counted 24, but I think I messed up. I said that too. Well, then I think you messed up too. All right. Here's what we're doing. We're getting into the nitty-gritties way more than we really need to, but
Well, now I need an answer.
yeah, we're gonna find out.
There's limit 24.
There's not. This is not gonna be anti-aromatic.
Let me show you how to count it.
Tell me.
Look at this. Let me show, I'm gonna come up there. Before you do that, let me show.
It's too late.
6, 12, 18. These ones are all just say just 6, 12, 18.
Okay.
20, 22, 24.
You missed this.
No, I didn't, because that would be here.
Then you missed this.
No, look. 6.
Linda, listen.
So you're
But
saying,
something is wrong, isn't it?
Well, okay.
so you're saying that because they're all benzenes, they have to be aromatic.
Let me make it
because they're
easier.
connected to each other.
Yeah, get out of my way. That'll make it easier on me.
Okay. Well,
Sorry. I need to.
Too general.
there's no organization here. Let me show how to do it.
All right. I decide when this is over, and it might be over soon.
There's a much easier way to go about it, I promise you.
I think I got it. No, I'm missing a pi bond there.
Here's what
Well, there's no charge on this structure. I'm gonna look up a different form. Did I draw it wrong? 2, 3, 2.
This is how I would draw the electron, John. Don't make it easier yourself.
All right.
Yeah, it's not.
Coronine is a polycyclic aromatic hydrocarbon. Where are you seeing it's not?
No, it doesn't have a
Here's
6 on each.
I figured out a better way. The internet helped me.
Okay.
Look at what's on the screen. That makes a lot of sense, doesn't it?
Can you have
Oh, yeah, I guess you're right.
2 half pi or p orbitals?
Are you turning more?
Pi electron?
Yeah, it's fine.
I wasted our time.
No, he did, but that's okay. No.
I mean, the
For this
tangents
class.
drive me crazy sometimes, so yeah, it's nice to stay on top of it.
Okay. Look at this structure on the board. How many pi electrons? You're still counting 24? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Okay, 24.
Great chemistry.
Maybe, yeah. 4n or 4n plus 2?
4
N is 5. 20 plus 2. Wait, no, that's not how math works.
Did anyone
All
talk
right.
to Huckel about this?
No, I don't think anybody has talked to Huckel about this. All right. So,
Is it crystal?
yeah, a lot of things are. Taking this sheet that we have, I want you to decide whether these compounds are aromatic, anti-aromatic, or non-aromatic. We'll say determine its aromaticity. Then I want you to circle all delocalized lone pairs of electrons. And to make this a little bit more interesting, I'm going to assign you into groups and have you just work on specific ones. Okay? I think groups of 2 to 3 is probably for the best. James, I'll have you and Nayira do adenine and serotonin on the top. Roja and Russell, proline and furane and THF, tetrahydrofuran. Cooper and Jamie, histidine, pyrrole, oxidiazole. Kayla and Christina, tryptophan, I think it's typo on tryptophan there. Imidazole and pyridine. Connor, Cameron, pyrozoline, cycloheptatrienol cation, cyclopentadienyl anion. And then I think you three all together, anthocyanin, oxirine, Oh yeah, just oxygen is good. All right. You can do it too if you want to. Determine aromaticity. Circle all delocalized lone pairs. Tell me. Yeah. Correct. Whereas this lone pair delocalized, which is why we can draw it like this, where the nitrogen doesn't have a lone pair.
Okay, why is that?
It allows for aromaticity.
So it's just because there's like another double bond in that,
Yeah, would you say that this nitrogen has a double bond? Yeah. The circle goes by it.
Oh, okay.
If the circle goes by it, it's in a double bond.
In this one, in my original notes, I don't know if I just caught it down, but like.
That's right.
It's not.
So you could redraw.
Double bond.
You could redraw pyrrole as this. This is the problem of Lewis dot structures. It's not a problem of aromaticity, and it's not a problem of us. That's pyrrole. It doesn't look like it has a double bond. That's pyrrole.
Those are the same.
Those are the same structure. We would say this approximately equivalent to each other. We say that because this is basically a resonance hybrid.
Helps that the other day he gave us
Good.
already, so everything that has that structure, we just know.
Aromatic.
The way it's drawn,
It's not fully conjugated.
Yeah.
It's not
I think it's a little
Only if you're gonna own all pairs because I can say pure.
makes sense. These ones are awesome.
I feel like,
Yeah, I think as long as you draw them.
oh yeah,
Ends already have the nitrogen on the
Yes, so it's fine. Okay. And mud dies. Or is it
The nitrogen with the meth, that one.
Are you saying that this lone pair
And the
is
other one's
delocalized? That's right. It means it belongs to the ring as a whole. So if it's delocalized, it's in what type of orbital? Right. Are you saying that this nitrogen is not already Yeah, Christina, did you check the notes for that? If you look back, we actually looked at purity yesterday. Or last time.
If you choose
Yes. Yes. Yes.
that's less, no matter
If it's pyridinal, that's what I call it. And that nitrogen is already in a double bond pyridinal. That lone pair is localized to it. It's in an sp2 orbital. If it's pyrrolian, if it looks like it should be sp3, but the compound is aromatic,
we talked about.
otherwise, actually
I
sp2
think this one.
to make it aromatic.
Wow, thank you.
What do you think, guys?
Oh, we said it was aromatic.
Freaking
Yes, because it's, we don't count it, so it's still have 6 hydrogens. That's what my notes say.
What did you count? The lone pair on oxygen? That's okay.
Because the plus just means there's
Oxygen's lone pair there can't be in the two orbitals.
I guess that means it has
So it has a few orbitals. By the double bond.
Alright,
So we
on the
can't
cycle.
put a lone pair there. What orbital is the lone pair? Yes.
You said this one was
Good work on that.
I
agree. Well, not a question mark here
Oh,
though.
yeah, makes sense.
So one of your questions is to circle localized lone pair. So which of those are delocalized?
That's the one we said was anti.
It is fully conjugated.
Yep.
Absolutely.
So were we right?
sp2, sp2, sp2,
Or I could be wrong.
Carbocation. or
Oh.
sp2.
Yeah, you're right. That one is aromatic. The negative charge is more.
I agree.
Yes, yes.
Hello, Rain.
More or less one below.
Okay, perfect. And then oxygen, this one.
You said there's 8, 2, 4. Oh, that's too late. Just one lone pair on the card. Yeah, there you go. That's what gives it a name.
So when we say it's aromatic,
If that lone pair doesn't delocalize, if it is delocalized,
or
does that make it aromatic or anti-aromatic? Then it probably is delocalized. Okay. Because it wants to be.
like
It wants that area. Exactly. Oh, okay.
because we kind of say
Yeah.
that there's like
Mhm.
so added.
Yeah, because we've got
They're not delocalized. They are localized.
Yeah.
Yeah.
I've actually got that.
These two are not moving.
Yes, sir. Not me. This is.
Yeah.
I was saying these.
I see. Yeah.
That's fine. This oxygen, I can use one pair of these. And that's what's giving this the sp2
Yeah.
geometry.
Yes.
But our
So means
was not because it was almost very charged.
That's okay.
But I thought, yeah, so that's not ever anything with resonance.
You can draw charged resonance forms. That doesn't mean that they're more favorable resonance forms. No, you would just no, because the structure is not net positive. The structure is neutral. You would just draw a circle.
See, I bet this is my.
What you wouldn't be able to do, Jamie, you wouldn't be able to draw pairs on opposites. If you do a circle, which is technically not,
Oh, you're considering are both. So you're gonna have. You presented that right.
if you draw a circle, you can't draw lone pairs.
At all.
No, because you're disobeying Lewis dot structure. So you just can't follow Lewis dot structure.
Does this not exist in the compound?
It does in several of the resonance forms, 4 of them, and a negative charge on a carbon or a nitrogen. If this forms, then there's a negative charge here, or this can push in a double bond and put a negative charge here, or this can push in a double bond and break this double bond and put a negative charge here. There's always a plus and a minus net neutral.
So the way it's written like that.
Net neutral.
But there's that. But there's no charge.
That's correct. So if you create a charge somewhere, you have to create an opposing charge somewhere else.
But this net neutral.
Takes no. Stability doesn't have to be the same.
Because you know with the carbanion, that sounds pretty much. That sounds way less favorable.
I'm confused.
That's okay. All resonance forms exist. A lone pair is delocalized. Your Lewis dot structure does not represent the molecule. Benzylic Lewis dot structure does not represent the molecule.
So you have to look at it the same way. Okay.
Yeah. Good.
Okay, that makes sense. I was getting the answer, but I'm not getting how I was getting it.
Good.
I was like, I don't know how it works. I don't know.
Great work. All right, guys, let's have a talk. I have to tell you something. I'm retiring. I'm just kidding. I was wrong, so I feel like retiring. I learned just now that Huckel's rules only apply to monocyclic structures. But the concepts generally can be applied to polycyclic. So this rule that I gave you here, just count all pi electrons, that works most of the time, especially for the compounds I'm going to give you. But it technically is not Huckel's rules. Here, for example, is this free online textbook, and it shows naphthalene, anthracene, benzo A pyrene, and coronine, all of which are considered aromatic. You can prove they're aromatic by testing their energy of combustion and seeing how much energy they give off against their non-aromatic counterparts. And they are aromatic. They're more stable than you'd expect, despite compounds like coronine having 4n pi electrons. So the examples I'm going to ever give you, the ones that are on your sheet, they do follow this. You're not going to run into a structure that breaks this rule. But you were right. There were 24 pi electrons, and it breaks Huckel's rules, but it's still an aromatic compound. And one thing I will say again is, if it looks like a repeating structure of benzene, it's aromatic. It will be aromatic. So we all learned something new today. Isn't it fun to learn? I've got this bump right here, which is where my stress builds up, and it just started acting up. So what does that tell you? I didn't want to learn today. All right. Adenine, aromatic or anti-aromatic? Aromatic. And how many lone pairs did you circle? Just one. And that's the one that I would call the pyrolean nitrogen. It's the only nitrogen that is clearly not in a pi bond. All of the nitrogens that are clearly in pi bonds, those are all already sp2. They already have a p orbital. Their p orbital is already consumed by the pi bond that they're in. their lone pair cannot be delocalized. They own their lone pair. That's what I call pyridinyl lone pairs. So here's the pattern. Nitrogen that's already in a pi bond, localized lone pair. Nitrogen not in a pi bond, delocalized lone pair. And what about serotonin? Has aromatic character. How many lone pairs did you circle? That pyrrolian lone pair on the nitrogen again. Proline. Non-aromatic. Why?
Because it's not conjugated.
Not fully conjugated. There's no pi bonds in that system, in that ring. What about furane? Aromatic. We looked at furane last week in this example. That's similar to the pyrrolian nitrogen. This is the furanian oxygen. Doesn't look like it's in a pi bond, but it shares one of its lone pairs. One of its lone pairs. The other lone pair has to consume the sp2 orbital.
Is it furan or furane?
I've always called it furane. What about tetrahydrofurane, THF?
It's
Non-aromatic, no pi bonds. Histidine. Aromatic. That's basically just pyrrole with a side chain coming off of it. And then you had pyrrole. Aromatic. And you had oxadiazole. What do you say for that one? Aromatic. Now, you did bring up an interesting question, Jamie, and I do want to explore it with you guys. Oxadiazole is basically furane, but two of the carbons have been substituted for nitrogens. But the number of pi bonds has not changed. So these nitrogens, their lone pairs are localized. They cannot share their lone pairs. Oxygen has one localized lone pair, one delocalized. And when we say a delocalized lone pair, we mean that you can draw a resonance form with that lone pair. How stable is this resonance form relative to the first one? Why is it less stable? Yeah, oxygen doesn't want that positive charge. Carbon doesn't want that negative charge. We have not minimized formal charges. So this is probably not the most stable. If anything, it's the most reactive form of oxadiazole. But we can still show a resonance hybrid for oxadiazole in the same way that we showed resonance hybrids for benzene and resonance hybrids for these other structures. Earlier, I showed this resonance hybrid for pyrrole, where it seems as if I do give a pi bond to nitrogen. Just not explicitly, it's just in that circle. At some point, it must have a pi bond. So I can do the same thing here, and I can represent my structure with a circle. The carbon-nitrogen pi bonds are gone. Well, not really. They're just in that circle. But this claims that there's also a double bond here, a double bond here between C and O, and a double bond here between O and N. How many lone pairs on the oxygen? I know. You can't say. By doing these circles, you are disobeying Lewis dot structures. So for the same reason that if you draw the resonance hybrid of carbonate, you can't draw lone pairs on the oxygens because your electron count is going to be off somehow. You could put one lone pair on that oxygen to represent that it has one localized lone pair. But do I put a positive charge on the oxygen? It has a positive charge in 4 out of 5 resonance forms. But no, I don't have to, because this represents all resonance forms, and all resonance forms are neutral overall. So I don't put any charges. It's weird, but that gray area between what a molecule is and how we're able to communicate it. That's the challenge.
Are delocalized lone pairs best drawn inside the ring?
No. Unless you're doing a circle. No, delocalized lone pairs don't need to be shown anywhere. You don't need to show delocalized lone pairs.
Well, you wanted us to do it on all of these.
I wanted you to circle them. But it doesn't matter where you draw them. Again, you're just communicating a molecule. Tryptophan. Or as I spelt it, the fan.
Is it a one?
Aromatic.
Aromatic.
You'll notice that it looks strikingly similar to serotonin. That 6-membered aromatic ring with the 5-membered pyrolean ring. Serotonin and tryptophan, they share a very similar ring there. Imidazole.
Aromatic.
Oh, and I meant to say, how many delocalized lone pairs on tryptophan?
One.
That pyrolean lone pair. Imidazole, aromatic. How many delocalized lone pairs?
One.
Just that same pyrolean type nitrogen, not the pyridinyl type nitrogen. And what about pyridine?
Aromatic.
Aromatic. How many lone pairs delocalized?
0.
None are delocalized. That nitrogen has to put its lone pair in an sp2 orbital because its p orbital is already taken. Pyrrolysine. I think that was you guys. No, in the back. Pyrrolysine. No one did pyrrolysine? That's okay. What do you guys say?
Non-aromatic.
Yeah, there's a ring structure, but it's not fully conjugated. What about anthocyanin?
Anti-aromatic.
Anthocyanin is aromatic. Are there any lone pairs? Sorry, lone pairs that are delocalized. The oxygen's lone pair is not delocalized. That oxygen is bonded just like pyridine's nitrogen. It's bonded like this, that oxygen is. Oxygen has a p orbital, actively being used in a pi bond. Its lone pair can't be delocalized.
Where is the pi bond in the middle there?
It doesn't need to be in the middle, but you can draw a resonance form that puts it in the middle. Draw a resonance form of the benzene ring, and just rotate each of them, and now it is in the middle. That's why you could just draw circles, too.
So
If you counted the lone pair on oxygen as delocalized, what would your pi electron count be? 18. No, we're not counting the other ring. 2, 4, 6, 8, 10. If you don't count the lone pair. 12. If you do count the lone pair, that would make it anti-aromatic. And this is a very common natural compound. So it's more likely that it is 10. It is aromatic. That lone pair, again, localized. Can't be in a p orbital. P orbital is already taken. Cycloheptatrienyl cation. Aromatic. Carbocations are always sp2. It's fully conjugated. Every atom in that ring positively is sp2. Every atom in that ring holds a positive charge, too. 1/7 of a positive charge. Cyclopentadienyl anion. Aromatic. Same number of pi electrons. Here, the carbanion may not seem like it's sp2 hybridized, but if it is sp2 hybridized, like the oxygens and like the nitrogens, then the compound becomes aromatic. Oxirene. Aromatic. 2 electrons from the pi bond, 2 electrons from the oxygen, 4 in plus. No, sorry. 4 in. Pi bond, 2 lone pairs from the oxygen, anti-aromatic. Nira.
So going back to the
Anthocyanin.
So it is aromatic, and we just ignore the that localized ring, and then we get 12 electrons.
So yeah, there's 2 regions of aromatic character.
Yes.
there's this benzene ring up here, and then also this tri-substituted benzene ring, and then also this ring that has the oxygen, this bicyclic structure, which we count, and we can still follow Huckel's rules, still aromatic.
That makes sense.
2 aromatic characters in that molecule. Bye, Jamie. Okay. How'd that exercise feel? You're going to do very similar things on your exams and your unit tests, where you have to decide what lone pairs are localized. Is the compound aromatic or anti-aromatic? So once you've forgotten all of these, download it again from Canvas and just try your hand at it one more time. See which ones come off easy and which ones are challenging for you. Before we leave, I want to talk about not before we leave, before we take a break. I want to talk about an interesting feature of aromaticity, which is that these compounds, which may seem strange to you, cycloheptatrienyl cation, doesn't seem very stable. It actually forms a lot easier than you'd think. Cyclopentadienyl anion might not seem very stable, forms a lot easier than you'd think. So I'm going to give you this comparison. Let's take cycloheptane and react it with a very strong base, sodium hydride. The products that we would expect here: cycloheptyl anion, that's not heptyl, excuse me, cyclopentyl anion with sodium and H2. How would we know how effective this acid-base reaction is? We need pKa values. The pKa of an sp3 hybridized carbon is in the 50s to 60s. The pKa of hydrogen, H2, is 36. Which of these is a better acid? pKa of 36, pKa in the 50s or 60s. 36 is a better acid, which means if these products form, no, they don't. They readily convert back to the starting material. That's to say, it's very challenging to steal an sp3 CH bond. Unless the product you get is an aromatic ring, in which case it's quite easy to get this. This is where I wasn't prepared. We're going to find out something new today too, together. Of course, this is a quiz question. This is great. That's exactly what I was hoping for. pKa of 36. pKa of 36. This was a pKa in the 50s for this hydrogen. This is a pKa at 15. Which way does the reaction favor? To the products. Readily favors the products. Not even a question. So how hard is it to deprotonate a CH bond? It depends. Do you make an aromatic compound? Aromaticity stabilizes the base. Aromaticity brings down the pKa, or the chance at aromaticity brings down the pKa. Does that make sense? These are the same bonds. These are very different conjugate bases. Now, a similar process for the cycloheptatrienyl anion. Let's compare this cycloheptatrienyl iodide with just cycloheptyl iodide. We know that this can dissociate to form a carbocation. But we know that it's going to have to form a carbocation that is stabilized by some polar solvent, partial charges that help stabilize that positive charge. This, on the other hand, doesn't need to wait for anything to form that positive charge, because in the process of dissociation, it forms our aromatic structure, cycloheptatrienyl cation. More stable, reacts more slowly, more reactive. That positive charge is localized. It's not sitting anywhere. Now, here's another interesting result of this. I don't know that I'll be able to find it.
Where's the free p orbital?
Decomposes. The free p orbital? Well, it's delocalized, so I just showed it delocalized. The melting point of the top structure, if it were bromine instead of iodine, is 203 degrees C. The melting point of cycloheptane is negative 12. This has a melting point, well, if it's bromine, 203. This has a melting point. I don't know about that. No, that makes sense. It's a liquid at room temperature. Does that make any sense? The difference in their melting points? No. What causes a melting point? What causes variation in melting points? Yeah. How strongly molecules interact with one another. How strongly do these molecules interact with themselves? Not very strongly. I mean, a little bit more strongly than water does. Water melts at, less strongly than water does. Water melts at 0. It takes more energy to get those water molecules to move around. It takes less energy to get these again, with bromine. Oh, I do apologize. That's not what I wanted, is it? I need cycloheptyl bromide. It's a liquid at room temperature and doesn't have a melting point. Well, that's just great. Let's just say it's around the same. It's probably a little bit higher, but we'll say that it's less than 25 degrees C. Why is it that it takes so much more energy to melt the top structure? The reason is the top structure is not just a normal solid. Do you know what else requires hundreds of degrees to melt? I'm sorry?
Just saying like
The pi bonds aren't causing this. Other things that take hundreds of degrees to melt are salts. Salts have melting points in the hundreds of degrees C. Caffeine has a melting point of 120? No, maybe it's 212. I forget now. The reason that this has such a high melting point is because it does readily dissociate because that cation is stable. Non-aromatic, not as stable as aromatic. So this compound has a tendency to dissociate and form more of ionic interactions between the aromatic ring and the halogen, which causes it to take a lot more energy to get it to melt. That's how stable these aromatic rings are. They lower the pKa and they increase the melting point. aromatic rings drastically change the properties of our compounds. All right, let's take a quick break. Take 5 minutes to move, get your blood flowing. Even if you're not going to leave the room, stand up for a little break. It wouldn't do this. No, it shares. If it shares its lone pair, this pi bond breaks and comes out as a lone pair on that carbon.
Because it's such an unstable structure, right? Is that because it's a trio?
No, what I'm saying is you can't have this.
Yeah.
You're breaking the octet on oxygen. If you form this bond, you have to break this bond. This is one of its resonance forms.
Got it. Okay, and that's okay.
Which is still anti-aromatic. And it's still unstable.
It still has the same count.
Correct. But you had this, which has 4 bonds to oxygen.
Yeah.
You'll never see.
Okay.
You'll only ever see 3 bonds. This would actually have a 2+ charge. If you gave this, it'd be 6 minus 1, 2, 3, 4, 5, 6. That'd be neutral, but it breaks its octet, which it can't do. Yeah, good question.
Or those windows could open.
Okay, the door opens and then it goes outside. I don't know if that's all the same to
Can
you.
we leave the door open?
It is cracked.
Like, as much as we can?
Yeah, but I don't have a way to do it. Things are gone. Oh, I'm jealous. That was the right call. She was walking the building.
Yeah, it's that time of year where it actually is nice to go outside.
No kidding.
This is that time of year where I wish we could just pause it for just a little bit. Enjoy it.
I know.
You're from Wisconsin?
Mm-hmm.
Yeah. Is it, do you have shortfalls there too? Or does it?
Well, I feel like literally the climate is changing.
Yeah.
So I don't know what they have anymore.
Yeah.
No, I remember having a long fall growing up. Like when school would start, we'd start, first or second week of August. You dress warm, but by September, you're dressing for cold weather until March, end of March, April.
So summer lingers a little bit here longer than.
I think so. This September actually felt.
Yeah, Utah lasts longer.
I didn't want to.
I felt like this September felt normal to me, where I was wearing flannels every day, needed a hat to get out of the house sometimes because my bald head is too cold. You know, like this felt like a normal fall to me.
Yeah.
I think I saw that it's supposed to warm up soon.
Yeah, I think it's supposed to get back up into the 80s.
Yeah. Indian summer is what we call it in Wisconsin. I'm sure that term needs to be phased out. I don't know why they call it that, to be honest.
But why would it need to be phased out?
Well, there were never an indigenous people here called Indians, so it's archaic.
What's in? Is it Illinois or Wisconsin? Here.
I don't know. I think there's more than one
Oh,
tribe,
there are.
more than one nation there. There's a reservation that I drive through to my family's cabin, and even that whole sentence just weighs so heavy. I don't know who they are. I've never stopped or anything. It's not like there's not a lot of
Open public business.
Not super obvious.
Yeah, actually, you can't tell. There's just one little marker that says entering the reservation. I want to say it's the Menominee Reservation. So I think the indigenous people in Wisconsin that are still still there are the Menominee. We have two Menominees, Menominee and Menominee Falls. And so that would make sense. Half of our words, though, are indigenous words. I could say them for you, but I think it'd be more fun if you guys tried to say them yourselves.
It's like somebody coming to Utah and trying to pronounce Wasatch.
Or Tooele.
I don't think that's an indigenous word.
It's fine. Tooele is weird.
Yeah.
How would you pronounce that?
It's way better.
Conomowoc. Obviously, Milwaukee is an indigenous word. Wauwatosa. It's a good one. Menominee. Menominee. Bum bum. I don't know.
That's just a form.
Wausau. Although I will say we might be butchering it. It's very possible the way that I grew up learning how to say some of these names is not how the indigenous name is pronounced. All right, are you guys ready? Were you trying to keep that material? To round out this section, I don't think there was anything on there you needed.
You can erase that.
Thank you. We're going to look at reactions. And some of these reactions are going to be review. Some of these reactions are going to be new. And I want to say, but the words left me. Oh, what I just mentioned and erased about those compounds that can become aromatic having very strange... Oh, this is something I wanted to show you. Deviation before the reactions. There are some strange properties. Your active homework has some compounds that go through that. Odd dipoles that you wouldn't expect. And it's because there are resonance forms that increase aromatic character, which means some rings are localized with electrons, some rings have electrons that have left in order to increase that aromatic character. What are those parts of DNA called? Nucleotides, right? The parts that actually do the binding. You guys might have noticed that I picked only one nucleotide to go on your activity sheet. That was adenine. And that's because when you look at adenine, it is the only obviously aromatic compound. This is another odd thing about aromatics. Carbonyls don't add their pi electrons. Not directly, anyways. Well, not at all, actually. Sorry for saying it. If you look at a compound like this, I believe this is called quinoline. You might say that every atom is sp2, fully conjugated, and that the pi electrons inside the ring are 4. Therefore, you would guess that this is anti-aromatic. But it's not unstable. It's rather stable. It's not aromatic. It's not aromatically stable, but it's not anti-aromatic. This compound is non-aromatic. The compound has decided to conjugate twice and leave these gaps in the conjugation. It's not fully conjugated, it's carbonyl and alkene conjugated. Isn't that odd? That stabilizes it more than trying to conjugate all the way around and only actually having access to these 4 pi electrons and being anti-aromatic.
Are they half aromatic?
Half aromatic is non-aromatic.
Are they delocalized on?
They're conjugated.
That does. So the black line isn't delocalized.
This is conjugation. This is break in conjugation.
Black line is not delocalized.
These 4 electrons are all conjugated with each other, delocalized.
Oh.
But the ring is not fully conjugated. But then you take something like, let's take something easy, like cytosine. Is cytosine a normal one? Do you guys know your nucleotides? Is it one that's involved in DNA? Okay, thank you. Cytosine, we've got this nitrogen on the top right, nitrogen on the bottom, and then connecting them is a carbonyl. Carbonyl at the top, double bond. I'm sorry, I was looking at thymine. Double bond to the nitrogen on the top, NH2 group up here. Can you tell me what functional groups are in cytosine? Amide, CO double bond to a nitrogen. Also, a second amide, CO double bond to a nitrogen. And alkene, if you consider this, imine, CN double bond. We're going to learn more about imines in our reactions. And amine. Amide, imine, amine. Pretty much the trifecta. This is a rather stable compound. There's a reason that life proliferates using a compound like this. It's rather stable. It can do reactions, some of you may know, but benzene can also do reactions. How can we draw the aromatic character of cytosine, even if it increases formal charge? Well, really, I've got this basic benzene type ring, but I'm missing a double bond here, correct? So let's form a double bond there. Nitrogen shares its lone pair. Oxygen has to take the pi bond back. What charges do I have now? Negative on the oxygen, positive on the nitrogen. Nitrogen shared its electrons, it should take on a positive charge. Increased formal charges, which should theoretically decrease stability, but it increases aromatic character. So maybe this is actually more like what cytosine behaves as. And wouldn't it be useful? Because right here, cytosine is able to hydrogen bond. That NH, hydrogen bonds with a lone pair on oxygen or nitrogen. And that O minus, hydrogen bonds with an H on something else. So by putting that more negative charge on the oxygen, you're increasing its partial negative, which is going to increase its ability to hydrogen bond. By putting a positive on nitrogen, you're straining this NH bond more, which it's going to increase its ability to hydrogen bond.
None of these are the forms in DNA.
Adenine is probably its form.
But where would a hydrogen bond?
Sorry, don't have a good answer for you there. All right, but and just to always rub it in my face that I can be wrong. Here's cytosine hydrogen bonding to something, and the nitrogen labeled number 1 is the one that I've just predicted. It's not actually hydrogen bonding to guanine. Is that what cytosine bonds to?
Yes.
Okay. So this this doesn't necessarily increase cytosine's ability to hydrogen bond here, but it could increase cytosine's ability to hydrogen bond here. The thing is, I've never heard a textbook address it. I don't have a good answer for you, but I do think it's interesting, and I have had bonus points, bonus problems on exams before where I say, draw a resonance form that maximizes aromatic character in this compound. And it's as easy as that. Even if it's not a more stable resonance form, not for you to decide, not what I'm testing you on, but just to say, look at this compound, draw a resonance form that shows the aromatic character that it could have. An interesting contribution of those carbonyls to these structures that aren't aromatic, but could be if their carbonyls were removed. Actually, I should have picked guanine. If you look at guanine in this example, to make an aromatic ring out of guanine, you do the same thing, but take this nitrogen, double bond it, push the carbonyl up to an O-. That's going to increase the hydrogen bonding at NH, increase the bonding at O-. So again, it's not in your textbook. It's a really good food for thought question. Yes, sir.
Why does the carbonyl only continue the delocalization on one side? Why not the other?
It's the most stable for it. You're asking about quinoline?
Mm-hmm.
It's the most stable for it. All right. Here are the reactions we're going to review and learn.
So anytime there's a carbonyl in an atom, it's not aromatic.
If there's a carbonyl in a ring, then that ring is not directly called aromatic, correct? But like I said, there are some carbonyls that you can show a resonance form that increases aromatic character. I'm going to abbreviate this radical halogenation here with pH and R. To be fair, I could abbreviate it with AR instead of pH because it doesn't necessarily need to be just phenyl. It could be a substituted benzene. But notice that the bromine goes to the benzylic position. Can you tell me a byproduct of this reaction? Br minus? What did you say? Yeah? Br radical. No, neither are quite right. HBr. So if you want to say Br minus, then also H plus. That's because the benzylic hydrogen is removed. So there's a byproduct here of HBr. Let's apply it to an example. And this time I'm just going to have I'll have a substituted structure. Can you predict the product?
There's two methyl groups coming off on the bottom.
Correct. Dimethyl. Good. Does that change anything?
No, I just want to make sure it's unit, right?
Okay. Where does the bromine go?
The top carbon on the right cyclic structure.
Good.
That's the benzylic one. The other benzylic carbon is already fully substituted.
No hydrogen to remove. Good. Bromine only goes here. Oh, I'm sorry. That's the starting material. Bromine only goes there because the other benzylic position has no benzylic hydrogen to remove. Yeah, bromine splits into radicals. One radical abstracts hydrogen and leaves a carbon radical. The other bromine radical terminates. There is a difference though. Why is it so stable? And it's because of resonance in that intermediate. When you get this carbon radical, that radical actually delocalizes throughout the benzene ring. That benzene ring still wants to reform at the end, but in the intermediate, it's just distributing the radical, lowering the energy, making it easier to form. So why does it not go here, which is also secondary? We could add a carbon. Why does it not go here, where it's tertiary? Because the benzylic position will delocalize it, make it easier to form.
What if there was also two methyl groups on that carbon at the top of the bromine lid?
If there were two methyl groups here, there's no benzylic position for it to go.
So the reaction just doesn't happen.
Yeah, it would. But it now goes to the next most stable, which is, rather than being conjugated intermediate, it'll be the most substituted intermediate, which is here, and those are different structures because of the alcohol on the ring. So you get two structural isomers. Okay. All right. Eventually, we're going to learn how to put bromines onto the ring. This reaction doesn't. So you will need to pay careful attention to what the reagents are to figure out where it's going to put a bromine.
I thought the radical separates the two bromines. Why? And
Yes. No. The light separates it into two radicals.
yeah, the light makes it two radicals, but why did you draw the radical on the compound then?
Bromine becomes two radicals. One of those radicals takes the hydrogen away via radical propagation. The radical ends up on carbon, right there. The second bromine radical bonds with that carbon radical. Termination. I'm not going to test you on this mechanism. That's why I'm not drawing it out. But you can find it. It's very easy to find, and that will answer your questions. When we look at alkene additions, for the most part, on these benzylic reactions, I'm going to show you carbocation intermediate reactions. The reason I'm bringing this up is regiochemistry. So if a reaction doesn't have relevant regiochemistry, then it's not relevant here. So like Br2, Cl2, those aren't really relevant. This is about regiochemistry. So predominantly, something like HX or H2O, H3O+. These are the reactions you needed to know earlier in the semester. And this gives you benzylic halides or benzylic alcohols. And in my example, I'm going to highlight why this is different than what you might have learned in OChem 1. In OChem 1, you learn to evaluate an alkene and decide which carbon is more substituted, which carbon is less substituted. Which of the carbons in this alkene is more substituted? Carbon on the right. The carbon on the right of the alkene has 2 bonds to other carbons. The carbon on the left has only 1 other bond. In OChem 1, we say the positive charge forms on the more substituted carbon, because that's where the positive charge is stabilized the most. That means that the hydrogen goes to the less substituted carbon so that the carbocation can form on the more substituted. But that's no longer true. Carbocation goes to the most stable position. That's the whole point. What's more stable than being delocalized with an aromatic ring? This carbocation has resonance forms with the aromatic ring. That make that positive charge delocalized and easier to form.
Is radical halogenation here 2 steps or 3 steps?
Radical halogenation is initiation, propagation, termination. 3 steps. Not all radical reactions are those 3 steps, but all radical reactions involve those 3 steps at some point. Any questions about this? Do you need to see more examples? It follows the same trend. And your homework should have examples on this as well. You know, this idea of having SN1 and SN2, it actually works better when we talk about rates of reactions, and I don't talk much about reaction rates in our class. So this may feel a little bit strange. I don't know that we're going to actually get into this much more. Let's say that I have this dihalide, and I react it with hydroxide. First of all, how can we rate hydroxide as a reactant? How can we classify it? Is it a nucleophile or electrophile, hydroxide? Hydroxide is a nucleophile. It donates electrons. Is it good at being a nucleophile or bad at being a nucleophile? Good. It's very good. Where does it want to go more? A more substituted position or a less substituted position? Less substituted. It prefers less substituted because as that nucleophile gets in close to the carbon, it's experiencing a lot of steric strain, spatial fight. So the more groups coming off of that carbon, the more it's got to push against in order to make that bond and break the other bond. The less it has going on, like if it's just hydrogens, the easier it is for it to come up and attack. So we typically say that this would favor substituting at the primary position, but we find that the aromatic ring stabilizes the intermediate. Yes?
Are all nucleophiles, do they all want to go with the least the substituted area?
No, not all, just strong nucleophiles.
Yeah.
Weak nucleophiles that wait for a carbocation to form, carbocations only form on the more substituted position. And this is what I've been saying for the last two examples. The aromatic ring stabilizes the intermediate. I'm not going to draw this one for you because it's less intuitive. I feel like you'd buy this. I don't know that you'd buy the structure I have to draw for SN1 and SN2. So this is just a good reminder that aromatic ring is stabilizing things here. These are new reactions for us. I didn't even number that one because I'm probably not going to test you on where is it going to substitute the fastest. But if you do go back to my old material, you may find problems that have that ranking on there. A new reaction for us. Wolff-Kishner or if you want to name it by the reagent, hydrazine reduction. We talked about oxidation reduction a little bit. Can you tell me what reduction means here? Gain of electrons. Who is gaining electrons? The starting material. To be fair, let's narrow in on a part of the starting material. You said the thing being reduced.
Not wrong.
Yeah, you are not wrong. You are not getting points for that.
Fair.
What do we care most about in this class? Points. Organic chemistry? Carbons predominantly, but hydrocarbons are a good answer. So when we talk about reduction, we're talking about reduction of carbons. How can I reduce a carbon? How can I give it more electrons? Keep in mind, carbon typically already has enough electrons. It's got 4 bonds.
Negative charge?
I don't need to give it a negative charge. That can reduce it, but I don't need to. Imagine I go from a carbon having 4 bonds to a carbon having 4 bonds. What type of bonds could I remove and replace them with in order to reduce the carbon? In the other direction, maybe, if you had alkyne to alkene to alkane, that's reduction. Do you remember in OChem 1, we talked about reductive hydrogenation. Alkenes go to alkanes. Not necessarily trading pi bonds for sigma bonds, although that's not a bad way to look at it. Not just any sigma bonds, though. No, good try. Bonds to hydrogens. If I replace bonds to more electronegative atoms with bonds to less electronegative atoms, carbon goes from losing electrons to those more electronegative atoms to stealing electrons from the less electronegative atoms. Carbon has been reduced only by nature of what type of element is bonded to it. So Cameron, your ideas were great. If I take an alkene and I add hydrogen across it, reduced. I've increased the number of hydrogens. But if I take an alkene and I add bromines across it, oxidized. I've oxidized the carbons. So it's not always pi bonds for sigma bonds. But here's a generic example. This reaction requires, or I'm going to say only works for CHO and COO. R. Do you remember what these groups are? What's the first one? A what? Not an ester, not an ether. Not enough oxygens for ester, not enough carbons for ether. The first one is not an alcohol, or I'd write it as ROH. Aldehyde. CHO is aldehyde. What about COR? Not an ether. A ketone. So this only works for aldehydes and ketones. All of the other carbonyls, ester, carboxylic acid, anhydrides, amides, nitriles, not going to work for them. And here's our generic reaction. I'm going to put R/H to say could be a ketone, could be an aldehyde. And what we get, the reagent we need is hydrazine and potassium hydroxide. Has anyone heard of hydrazine before? Christina, do you have in your engineering classes?
It sounds so familiar, but I don't really know why. I feel like Martian. He makes it a little bit.
Who?
In The Martian.
Oh.
Yeah.
I bet it'd be a good fertilizer.
I forget why he makes it, but there's
Or fuel.
the whole drama of him making it.
Interesting.
So you hear the word a lot.
I think hydrazine is highly explosive. I think it's
Yeah.
dangerous to work with.
Causes some problems in the plot.
But here, hydrazine is both a nucleophile and a leaving group. The product that we get will shock you. What is that? That's an alkane. We just took a carbonyl to an alkane with hydrazine. So I think the hydrazine reduction makes a lot more sense. It is important that it's basic. Without basic conditions, you actually get an imine, CN double bond. With basic conditions, you're able to kick this off. Some places, you may see hydrazine written as N2H2, and that's okay. I don't like it quite as much. There are two byproducts. Do you think you can guess what either of them are? Water is one of them. The oxygen of the carbonyl leaves as water. Where did those two hydrogens come from? I'm sorry, I wrote this wrong. It's not into H2. I apologize. Into H4. Two of the hydrogens came from hydrazine. Where did the other two hydrogens of hydrazine go?
On the bond.
To the carbon, because it becomes a CH2 group. The other product is nitrogen gas, N2. Good work. It makes sense that N2 is a product here. N2 is very stable. So it wants to form and it wants to leave. Just like you all. So let's do an example problem.
It doesn't work for double bonded nitrogens?
I'm sorry?
If there was a nitrogen instead of an oxygen, would it work?
It is a nitrogen.
No.
Oh, no, it doesn't work. Sorry. Actually, Killian, there is an intermediate where this is CNH with a double bond. So technically, yes, it does work. It's part of the reason it works. What's the product? Draw it out. What are you wondering? Do I reduce that carboxylic acid or not? Well, there's two things. We said that this only works for aldehydes and ketones. And that carboxylic acid is not Benzylic. Right?
If you did have like a reaction of this where S is staying in a basic state, and let's say again you got a ketone, not carboxylic acid, would it then do the reduction of both of them?
Okay, sorry. So you know what? I can add this. We can elongate the structure a little bit. Let's put a ketone down here on another carbon chain. Does that answer it? What if there's a ketone where the carboxylic acid is? What happens to that ketone? It's not benzylic. Once again, the aromatic ring is stabilizing these reactions. Oh no, I'm sorry, but this is tricky. I did forget, because your textbook never really addresses this either, so I only just learned this in the summer. It does reduce all aldehydes and ketones.
Okay, so it just would continue. So I guess then like
This is a good example
this
for
is
us.
one where you would need multiple parts. Like it wouldn't have to be like 2 parts or like times 2. It would just have this.
Yes, correct. I'm not going to tell you how many equivalences you need, but notice that both ketones are gone. Yeah, I agree.
Benzylic would go first because it is the most stable, and then the other one would go second.
Probably, yes, but you're not going to be able to isolate it. It'll go. They'll go. So they your textbook introduces this here, even though it's not intrinsically benzylic, but it's going to become useful in the next chapter.
So it's not going to need 2 equivalences to take both ketones away?
It would. But to be fair, hydrazine and the catalytic base, those are going to be in excess anyways. So we're not going to assume one equivalence. We'll never assume one equivalence. We'll assume complete reduction.
Wouldn't it still work with only 1 equivalence and you only have nitrogen gas as a byproduct? Because there's the 2 H2 groups.
Yeah, but if H2N and H2, if hydrazine is in excess, then there's enough to keep going. And then you get 2 equivalences of water, 2 equivalences of nitrogen. Yeah. So we do have to assume excess of hydrazine.
If you're forming a molecule and you're going to remove 1, would you then write 1? Or is that just illogical because that's not what would happen in a molecule?
It's challenging to control that, but what you can actually do is protect one group via different chemical reactions, then reduce the one you want, and then deprotect it, reverse a chemical reaction. We'll actually look at protecting aldehydes and ketones so that we can do reactions to carboxylic acids and stuff like that. So, you have a question? Can you show me the reduction of benzaldehyde to toluene? Using Wolff-Kishner. This is testing you on what? Nomenclature. Benzaldehyde. I guess that's kind of a weird way to draw it, to be honest. I'm just going to put PHCHO. But you could draw a ring and a carbonyl. That's all accurate. Toluene. PHCH3. CO double bond is gone. 2 hydrogens are added in. Benzaldehyde to toluene. All right, we'll pick up with Clemmensen reduction, which is exactly the same but uses different reagents. And then benzylic oxidation before we start looking at aromatic substitution reactions, where we can start adding things to the ring. We'll do that tomorrow, next class, and next week. And we're going to be doing mechanisms as we get into those reactions. Have a great night, guys. Thank you for your time. I'll see you next class.